Alright, so we might be a little fuzzy here, but we'll try to make it work. Okay, so this section is 3.3, log functions and their graphs. And, man, that's awful. Sorry, guys. Doing the best I can here. So we're going to talk about first how logarithms and exponentials are related. And basically, well, I'll show you rather than tell you. Alright, so I'm going to graph in blue, and I'm going to graph a log in red. Let's see if you notice what the relationship is. So remember we talked about our basic functions. One of our parent functions was e to the x, and it looked kind of like that, and it passed through the point 1. And then a log graph, the natural log, was also one of our basic functions. Looked like this. Also passed through the point 1, but on the x-axis, not on the y-axis. What do you notice about the graphs of those two? Yeah. They're inverses of each other. Right, exactly. If I put this line y equals x right through here, okay, they're reflections of each other over that line. Those are two inverse functions. So that's important. Okay, and this is true of any log and exponential that go together. But as far as the parent functions are concerned, e to the x and natural log x are inverses. Man, that's fuzzy. Sorry. So think about that for a second here. So the way that we do an inverse is if I had like y equals e to the x, and I wanted to calculate its inverse, what's the process that we took to do that before? Change the x and the y, right. So we'd switch that to x equals e to the y, and then try and solve that for y. And like we talked about yesterday, if you log both sides of this thing, then you can get rid of the base on the one side. So because it's e, if I do a natural log to each side, I get natural log x equals natural log e to the y. And then natural log of e to the y, there's this property that we use, we kind of mentioned yesterday, which we'll talk more about in the future, but we can bring the y down in front, and then we have y times the natural log of e. Okay, so here's a little property we're going to talk about a bit today, but see if you remember it. What is the natural log of e? It's just 1. Yeah, exactly. So we end up with the natural log of x equals y, or if we just switch that around, y equals natural log x. So we've shown that this is the inverse of that. Okay? So what that means is we can switch from one to the other then. Okay? So in general, and this is where this rule comes from that we talked a bit about yesterday, and this is for any log. So if I have y equals log base b of x, then I can switch that around so that x equals b to the y. And that's kind of my little conversion rule from one to the other. Okay, so that lets me do that. So if I have an equation written one way, to solve it, I might want to rewrite it a different way. So, and also, to evaluate some logs, it becomes a case where we might want to switch these things around too. So we'll do a few examples of this and see if you can just, to start with, just take the expression that I give you and take the log and see if you can rewrite it back into exponential form, just so we get used to this. So log base 2 of 8 is equal to 3. So what would that be then as an exponential? Yeah. Mm-hmm. Okay. So, and that should make sense, right? 2 to the third power is 8, right? So then log base 2 of 8 equals 3. So it's kind of unraveling this to write it that way. All right, so let's do one where I won't tell you what it's equal to and see if you can tell me by doing this kind of a trick as well. So let's do log base 3 of the square root of 3 equals x. And I want to figure out what value of x makes that true. And we might not be able to do it just yet in our head, so switching that thing to an exponential might be an easier way to help you see what x should be. So for this particular one then, what would be the exponential equation that goes with it? Yeah? Okay, so 3 to what power gives you the square root of 3? Yeah?
1/3.
No. You got the right idea, but I think you maybe just misspoke. Yeah? 1/2.
Oh, yeah.
Right? Because we said before a square root is a 1/2 power, right? So if it's 3 to the x, square root of 3, yeah, it should be 1/2. Okay, let's try another one. See if we can do this kind of the same idea here. Log base 5 of 1 over 25 equals x. So can we evaluate that log by switching it into an exponential as well? So somebody who has not spoken yet today, let's switch this one up. Yeah, Isaac. All right, 5 raised to the x equals 1/25. So 5 squared equals 25. So 5 to what power is 1/25 though? Yeah, -2, right. Okay, so what this allows you to do is to evaluate some logs. Now, do you have to do it this way? Not necessarily. There are some properties of logs that we will see that'll allow us to get through some of these problems as well. And that's what we want to do next is just kind of list out some properties. You've probably seen all of these before. It's just a matter of recharging your memory here. And then these will be things that we can use as well to help us evaluate some of this log stuff by hand. All right, so the first one, properties. All right, so the first one would be log base b of 1. So no matter what the base is, if you're doing the log of 1, what does the answer have to be every single time? 0. Yeah. Okay. Now, to prove that to you, why that's the case, I can switch this into an exponential and show you. Okay? If I have log base b of 1 equals 0, that would be b to the 0 equals 1 written as an exponential. Does that make sense? The exponential piece at least? Anything to the 0 is always 1, right? So no matter the base, raise it to the 0 power equals 1, so the log base b of 1 should equal 0. All right, this one's probably the most useful. Log base b of b, what should that be every time? 1. And again, I can prove it to you using an exponential. If I switch this one into an exponential, this would be b to the 1 equals b. All right, this base b raised to the first power equals this b, right? So anything to the first power equals itself, so the log base b of b, no matter what that number is, should equal 1. So that one will work too. Okay. Another one, log base b of b to the y. What do you suppose that one's going to be every single time? It's equal to y. Mm-hmm. All right, so if I switch this into an exponential to prove it, see if you can follow me here, okay? So this b right here is the base right here, b, raised to this y is equal to what's in the log, b to the y. So it's the case because b to the y equals b to the y. All right. In this one right here, we were really doing that same thing, weren't we? If this doesn't have a power written on it, what's it assumed to be? 1, right? So log base b of b to the 1 equals 1. That power should match what it's equal to. So if this was like squared or something, this would come out to 2. Okay. And then doing this same kind of thing, these two kind of go together. If I was doing log base b of b to the y, there's a property we talked about where you can take this y and bring it down in front. So y log base b of b. Okay? So in doing it this way, do you see how this still works out to equal y? Because what's the log base b of b? 1, right? So y times 1 still gets you y. Okay? So sometimes, rather than just going directly to this, you might want to think about bringing this down in front if it makes more sense to you, and then you can evaluate it doing kind of the same thing. Okay? So thinking about those properties, let's see if we can evaluate some of these other ones. And if you want to switch it into exponential like we did with those other ones, that's totally fine. Or if you'd rather just use one of the properties and do it that way, that's fine too. So let's see if we can do some evaluating here. All right, so we'll do another one. All right, so we've got 4 of them here for you. Log base 8 of 64, natural log of 1 over e, log of 0.01, and log base 2 of 1 over the square root of 2. Okay, so the first one. Is there a way that we could rewrite this first one so that it like matches one of those properties we just talked about and we can get the answer right away from that? Anybody have an idea? Yeah, go ahead. Oh, so you're going to do it to x and make it exponential? Sure, that works too. I was going to do it a different way for a second, though, just so people could see it, but you're absolutely right. You guys all see what I did there? I made 64 8 squared. Okay, so what property can I use now? Right, so what should this one be? 2. Yeah. Okay. Or, like Josh was saying, if you want to switch it into an exponential, it would have been 8 raised to the x equals 64. And that one makes a lot of sense too, right? 8 to what power gives you 64? 2, right? So that would be 2. Okay, what about the second one here? Natural log. What's the base of a natural log? E. Okay, so you're going to see probably a lot of natural logs of things involving E because of that. So is there a way I could rewrite that log expression to help me out with that? Yeah.
Natural log of e to the negative 1.
Mm-hmm. Natural log of e to the negative 1 because it was in a fraction there. So what should this be equal to then? Using the same property as the last one. Negative 1, right. Okay. The next one, log of 0.01. Well, it's probably going to be easier to rewrite that one as a fraction in this case, so we can kind of see what's going on better. So what is 0.01? What fraction is that? It's 1/100th, right? So this is the log of 1/100th. Okay. Now, what's the base of this log right here, though? 10, right? It's called a common log. You guys remember that from Algebra 2? All right. Common logs are base 10. So if you see no base written, assume 10. Okay. So I'm going to go one more step with this one then. So log, if it's 1/100th, that would be 10 to the negative second power, right? So what is log of 10 to the negative second? -2. Again, using that same property we used in the first two. All right, and then the last one, log base 2 of 1 over the square root of 2. Anybody come up with a way we could rewrite that one to get it going? Log base 2 of something different that's more helpful? Yeah, go ahead.
Log base 2 of 2 to the -1.
Good. Yep. Does everybody see why that's -1/2? There's two things going on there. It's a square root, first of all, which means it's a 1/2 power. And not only that, it's in the denominator. And if it's in the denominator, it's negative. So it's a -1/2, but still base of 2 there because there was a 2 in the square root. So what's the answer to number 4 then? -1/2. All right, so I'm going to expect you guys to be able to do this kind of stuff. Okay, if I give you some kind of a log where you can make it so that the bases match, you can evaluate those logs by getting at the exponent there like that, using that one of those properties we talked about. Okay, so that's kind of the first bullet, or the first two bullets that I wanted you to be able to do, is to convert between log and exponential forms, understand the basic log properties and use those to evaluate stuff here. And then also in simplifying log expressions, it's the same kind of thing here too, doing this same idea with those properties. So what I want to do for the rest of the time that we're here is talk about graphs of logs and how we can kind of compare them and that sort of thing and do some transformational work. And after that, I think we'll be good, or we'll be all set for today. So it's important to know kind of what your basic log graph looks like before we start doing any of this stuff. So we're going to review that basic function here for just a minute. When we first started today, we graphed one of these as well. But no matter the base, every log has the same basic shape to it unless we do some kind of transformation. And it looks like this. And it'll always go through the point 1. So this curve is a graph of y equals log base b, it doesn't matter the base, of x. Could be a natural log, could be a common log, could be log base 2. They all look like that. Okay? So I might ask you to sketch a graph of a log that has some transformational stuff happening to it, but this is going to be kind of our home base, okay, where we start from with all of those. So we're going to do some sketch graphs of some logs, and I'm going to take a log of some various base and just do something to it and see if you can figure out what it should look like. So let's start with this. Y equals negative natural log of x. So based on what you guys know about transformations, what should this look like? How is it different from the log graph that we started with up top? Exactly. Right. It's a natural log. The natural log looks just like the one we started with, but we have a negative in front of this one, so the only difference is it's going to have a reflection over the x-axis. So it's going to come down kind of like that. And still, it should be passing through that same point, right? Because it's on the x-axis. So at 1, it should be going through there. So that's a sketch of negative natural log x. That works. All right, so what about y equals log of x plus 3? So how does that change things? Yeah. Goes left 3. Okay. So think about this graph at the top here, shifted to the left 3. Okay. Do you see how this graph has a vertical asymptote right down the y-axis? Where should that vertical asymptote be now? Negative 3. Exactly. The asymptote's negative 3. The intercept will be negative 2. So it's going to be over there now, and it's going to have the same shape. It's going to come up off of that, doing that kind of a thing. But yeah, so the question is then, this point right here, it used to be at 1, so now it should be negative 2, right? So that would be an okay sketch for that one then. Okay, just making sure that the asymptote is clearly labeled and the intercept is clearly labeled. We're good. All right, let's do a couple more. So how about something like that? 3 plus log base 2 of x minus 1. That's a subtraction. So what's happening with this one? What kind of transformations have I put on this time? Yes? Yep. Yep, it's going to shift to the right 1. And then what's that 3 in the front going to do for us? Yeah. Up 3. Okay, so we need to move it up 3 and to the right 1. So let's start with the asymptote. That's kind of a nice little home base for us here with these. Where should the asymptote be now then? At 1. Okay, so I got the vertical asymptote at 1. And then it's going to go up that asymptote, but everything should be shifted up 3. So normally we would have a point right here, right? It'd be over at 2. But because we've shifted everything up 3, we don't have that ordered pair anymore to rely on. It's actually up here. And what should be the coordinates of that point? Careful. 2, 3. Yeah. Okay, so when you sketch these graphs, I want to see that point somewhere on there, okay? Whether it's still an x-intercept or if it's been moved up or down based on a vertical shift, make sure it's still there. Good. All right, so last one. See if I can make this one a little trickier. These always throw people off. Natural log of 2 minus x. So what's happening on this one? Yeah. It's always the question, is it right or left after you do that reflection? Because it's a little confusing. And honestly, it depends on what you do first. The order matters on this one. Okay, Josh, you got a question?
When you reflect it over the x-axis,
It's not over the x-axis. It's over the y-axis, right? Because the negative's on the x. Okay, so let's think about it this way. We're going to go over to the side here. Let's do some things in order. We're starting with natural log x, right? That's kind of our parent function for this one. So what would be, well, you tell me, what's the first thing you want to do? You want to do the reflection first? Seemed like everybody was talking about that first. So you want to do that first? Okay. So then the first thing, if we just do the reflection, it would be natural log of negative x then. And then if I want to make it 2 minus x, am I subtracting 2 or am I adding 2 to what I have? You're adding 2 to it. Okay, like that. But remember, whenever we do something horizontally, we want to think about doing a substitution for x. So if I'm writing this thing as negative x plus 2, if I was actually substituting for x, wouldn't it be this? Think about going from this one to this one. If I wanted to replace x with something to make it equivalent to what that is, wouldn't I have to replace the x actually with x minus 2 because that negative would have to get distributed in there? So really what I've got going on here is y equals the natural log of negative x minus 2. So we did our reflection. What actually happened here, though? Was it to the left or was it to the right? To the right. Yeah. That's why these are confusing. If you want to avoid the confusion, do the reflection second. It's much easier. But it can be done this way. It's just you have to think about substituting for x rather than just tacking on a plus 2 next to it. Okay? So what we've got going on in this graph then is we want to reflect it over the x-axis, or over the y-axis first, and then move it to the right 2. Okay, so after the reflection, it's going to look like this. So I'll just do this one kind of light. And then we're going to scoot that over to the right 2. So where would the asymptote be now? Positive 2, right? Because we're going to move this thing to the right 2. And right now, the asymptote is still down the y-axis. But moving everything to the right 2 would put that asymptote at 2. And then it's coming up like this. And where would be that point then? At 1. So the graph should look like that. Okay, so not this one. That was just our little first step, but the solid one we got right there. Okay, so just be careful with the with some of those. If they have the minus x, those are kind of like the dreaded ones. But you can do it. Okay, I'm going to stop there. I'm going to let you guys get to work on this stuff. I'll let you know, there are some that are just punch it in the calculator ones, and yes, they're as easy as you think. So don't overthink those. I got some of those mixed in there.